A very pleasant evening to all distinguished panelists and participants. Bharati Vidyapeeth's Institute of Computer Applications and Management, BVI CAM, in association with Computational Intelligence Society, CIS chapter of IEEE Delhi section, Computer Society CS chapter of IEEE Delhi section, Technology and Engineering Management Society, TEMS chapter of IEEE Delhi section, System Man and Cybernetics SMC Society chapter of IEEE Delhi section, Communication Society of IEEE Delhi section, Consultants Network Affinity CNA Group of IEEE Delhi section, Life Member Affinity LMA Group of IEEE Delhi section, Inter-Society Relations IRS Standing Committee of IEEE Delhi section, Industry Relations and Special Interest Group on Humanitarian Technology, Site Standing Committee of IEEE Delhi section, Region 10 of IEEE with the associations of Computer Society of India, CSI, Institute of Information Technology Professionals, IITP, ISTE Delhi section and IETE Delhi Center as technical collaborator welcomes you all today to this IEEE IETE BVI Camp Technical Lecture Series on Quantum Age, Connectivity Redefined. With immense pride and honor, we are delighted to announce that we, with united hands, mark special contribution for the monumental occasion, Golden Jubilee celebrations of the IEEE Delhi section. From 13th May 2025 to 12th May 2026, we mark 50 years of this vibrant and pioneering section, a journey that began in 1976 and has since ill-shaped the technological and professional landscape of Northern India through innovation, collaboration, and learning. This webinar is an initiative to celebrate this legacy. According to Cynthia Sue Larson, the quantum age takes us far beyond the information age to a way of living in which we delight in uncertainty, thrive in entanglement, and flourish with an awareness of many possibilities. Imagine a future where Mars rovers relay real-time data to the Earth, deep-sea drones coordinate across oceans, and interplanetary missions maintain seamless contact. This is the purpose of quantum communication. Unlike classical system, quantum communication leverages the principles of quantum entanglement and superposition to enable ultra-fast, ultra-reliable, and inherently secure data transfer across vast distances. Its resistance to interception and tampering makes it ideal for protecting sensitive information in critical application. This webinar explores how quantum mechanics is redefining the foundations of communication, from global quantum internet to instantaneous synchronization of distributed AI systems. We will delve into the transformative potential of quantum networks and why they are essential for the next era of autonomous system, space exploration, and beyond. I would first take this opportunity to welcome amongst us our distinguished panelists for the day. We are privileged to have amongst us a galaxy of experts. I would first now welcome amongst us our expert speaker, Mr. Shubhankar Pal, sir, with an e-bouquet. Welcome to the session, sir.
Thank you so much. Thank you for having me.
The pleasure is all ours, sir. Mr. Shubhankar Pal, sir, is a Senior Director and Global Innovation Leader for Intelligent Networks Program in Cape Gemini Engineering. He has close to 25 years of experience in the telecommunication industry. His responsibilities include technology product incubation, product strategy, and roadmap development, consulting and service offer definition for telecommunication and related markets. His interest area include advanced network automation, optimization, and sustainability using cloud-native principles, and machine learning for 5G and beyond networks. Before joining Cape Gemini, he worked at Nokia Networks and C. Dot. We are honored to have you amongst us, sir, and I would now request you to kindly enlighten the house. Over to you, sir.
Thank you so much for this, and quite excited to be here presenting this very interesting topic and a kind of very new topic that we have in the communication space. Just if you can please let me know if my screen is visible to all of you.
Yes, sir. It's perfectly visible.
Okay, thank you. So today I'm going to talk about quantum communication. So communication has always been the underlying platform for the digital world, right from the very like ancient time. The communication was there, and it has been evolving over a period of time. And then we saw the revolution of digital communication that has helped this smart robots, smart cars, etc., to be connected. And now from the digital world we are moving towards the quantum world. Again, quantum is quite far away, but there is tangible research that is happening already, and some of them I want to bring it here. So okay, so let me just start going to the next slide. Okay. So before I move forward, I want to thanks to my team members who helped me to put this presentation together. There's a lot of research that has gone into creating this slide. First of all, I want to thank Tanmay, who is our lead architect for network AI and quantum communication. He is based in Gurgaon office in Capgemini Engineering, same office I am, and he has been the most of the content that you see here, he has been researching, putting it along with me. And I will also want to thank Mary, who is in Bangalore office, and she's the product manager of network AI, 6G, and the quantum communication. So without their help, I could not put this presentation together. Okay, so before I start and talk about what is content communication, I just wanted to give you one recent, very recent example, not like even a year old, it is just a month old, where not even a month old, in this month itself, where uh, IIT Delhi, in collaboration of DRDO, has shown a quantum communication in free space, and that is a big thing because we are not talking about a communication happening in optical fiber or in a closed door system. It's an open space in IIT Delhi's campus, very next to where I am right now, and they showed a completely secured communication based on quantum principles. Don't worry if you don't know the quantum principles. I will talk more about that in the subsequent slides. But this is a big leap for India in the quantum world. Our defense minister, Sir Rajnath Singh, has also congratulated the team, because here, if we have this kind of secure communication in a free space, that means nobody can tap into the sensitive defense communication that is happening. So it's a big thing for us already. So on the onset, I want to establish that we in India are not far behind from the other part of the world. We are actively contributing, testing this in a partnership with our premier defense institutes and the academic institutes. Okay, so before getting into quantum communication and the nitty-gritties of what quantum communication is, let me just go back to our old days of classical physics and why this even quantum physics came into picture. You know, so classical figures, we know the great theories of Newton for gravity and motion. So anything that is to do with the objects, the large objects that is around us, and the mechanics of those, like how they move, how they interact with each other when they are moving. That is, like, or I should say that something which is larger to the 10 to the power 9, 10 to the minus 9 meter, comes into the domain of classical mechanics. That means you're talking about macro objects, objects that we see with our eyes every day, and how they are moving. So, and this has like helping us to like uh, create those different innovations that we are already seeing today in the industry. But what has become more and more evident now that we cannot just stop by with the innovations and the work in the macro world. We have to also move toward the micro world as well, which is that the particles which are less than 10 to the power minus 9. What does this mean? It means we're talking about the electrons and photons and how they are behaving with behaving in a optical fiber or a free space communication channels, and just controlling those systems, like the atoms, electrons, and photons. That is helping us to go to the next era of like a communication, next era of computing, next era of how we are innovating. So that way, you might have heard about these quantum computers. You might have heard about the secure cryptography that we're talking about. Uh, we just had an example in the previous slide as well. So all these giant innovation that we're doing in the that will be mainstream in the next 10 to 15 years, that will fall into quantum mechanics. So when you are talking about things which are extremely so small, we cannot see with our own eyes, but they are helping us to create the next generation of computing, next generation of communication, next generation of security, and their understanding their behavior and their kind of relationship with each other. That is what quantum mechanics is all about. So, and it is not new. The quantum mechanics have been there for a while. It was there, I think, even before 1990s. And then we saw the first revolution in 2000 when we saw some of the basic quantum lasers coming in. But the real evolution that happened, or I will say the second revolution of quantum happened now in this period, where we are seeing those giant quantum computers coming in and the kind of the magic they are doing. I will say that we are in the second phase of quantum revolution, and that is where all this that I'm talking about is taking place right now. Okay, so why this is important? Why when we should we need this quantum computers, we need this quantum communication, and so on. So this is a very nice chart that was created by one of my colleague in Capgemini, and it tells you from an era of 1965 to 2025 the number of instructions that were processed by a computer. So when like initially we as human landed on moon, the kind of instructions that were processed by computer were 10 to the power 10 kind of instructions. When the first AI based computer that came in that could challenge a human chess player and could even beat Gary Kasparov in one of his own games, and that then we are talking about something around 10 to the 15 instructions. Then the advent of the modern era AI, the neural networks, the machine learning that we know now, we're talking about somewhere between 10 to the 15 to 20 to the 20 instructions. And now we are in the world of generative AI. We're talking about GPT-3, GPT-4 now, and we are talking about somewhere between 20 to the 20 to 20 to the 25 instructions per set. So you see that like with the passing time and the passing centuries, the number of instructions that are required by the computers to process is just getting more and more. So these classical computers, though they will still be there for all our need. Like when you are talking, we don't need a quantum computer. But some of those research on say drug discovery, research on say finding the new set of crops that can be grown in a smaller set of land, but the amount of or the volume of crop that can be generated is much more than what we're able to do today in agriculture, the space communication and so on. So that needs a completely different kind of compute. and that need a complete different kind of volume of instruction that has to be processed. And that is one of the need of why this why we are getting into this quantum era, why we are looking into this quantum particles which are extremely small and trying to control them so that we can get this power out of these things, you know. So that's one of the reason I will say that why we are just so interested in the quantum world. So there are few things in quantum we should see, and I will just have some examples. Don't get confused if you don't understand. I have plenty of examples that I will talk about, but there are a few things that we should know before getting more deep into quantum communication. One of the thing is superposition, you know. So today, you know that when we like use our computers, the instructions are converted into bits which are 0 and 1, and a bit can be at any point of time in one of these two states, you know. It can be either 0 or it can be 1. It cannot be both at any point of time. But in quantum, we will not have bits, we will have qubits. No? And the interesting part of qubit is the qubit can be 0 and 1 at the same time. Bit confused? Let me give an example. That whenever we said toss a coin, when the coin, before tossing, I know whether it is head or tails. After it comes back to my hand and I see it, I know that it is head and tails, right? So it will be one of these states. But when it is spinning, or when it is my hand but I have not opened my hand and not seen what is that has come in, so it can be either heads or either tail. That can be, it can be both, you know. And that is what superposition is, you know. If one qubit can be both in 0 and 1, and that gives the power to the system, and the huge compute power this quantum computers are bringing in is because of this. Let me give an example that I've seen. Say we have a 4-bit password, you know, like, and I am a hacker, and I want to maybe I'm an ethical hacker, maybe I don't want to do wrong thing, but I want to hack that password. Now, if it is a 4-bit, then I can be in one of the, so I have to try all of these 16 combinations. So 4 bits means 2 to the power 4. That means 16 different combinations are possible. And all these combinations you are seeing on the screen. And you will have to like try one at a time in a classical computer to see that which of this password is actually matching. So how it will do, you will take say one of these combination, send to the normal computer and try whether you're able to open it or not. It will say no, that means this password is wrong, and you will keep on doing it for all these combination until you find one of this combination. So one, that you are doing all serially, that means one after the other, and only when one fails you can submit the other. You cannot do things parallelly. But now if you remember what I told about the qubits, qubits are the bits in the quantum world, that it can be 0 and 1 at the same time. So what I'm saying is that if it is a 0 and 1 of the same time, this all the 16 possibilities I'm giving at the same time, and that means one of them will the right is also there and the wrong is also there. So that way, in only one instruction, or only in one combination, or like one entry, input entry, it can find the password. So it will not have to go through this 16 combination. Just one combination it will be able to find out. Doesn't it look like a magic? Yeah, but you may ask me then, what is the right password? How it will know? So there are some complex, so there are some algorithms called Grover operator that will, using an interference, it will just remove all those wrong operations and bring the only the right one. But the most important thing here is that I am not giving 16 combinations. I am just giving one combination. So it is only with 4-bit. Imagine that if there are 300 bits. So it will take millions of years for a long normal computer, even in our whole lifespan, will not be able to solve the problem. whereas that can be solved into using a quantum computer using minutes using this superposition theory. So this is one of the key important thing in quantum computing world, which is making the quantum computers very fast and all the associated technologies, and one of them is quantum communication, also extremely fast. Uh, So so this is an magical thing, I will say, that quantum computers are bringing in, and which will help us to see how the next generation communication is evolving. Okay, so I hope you understood superposition, where the qubit, which is an alternate to bit in the quantum world, can be both in 0 and 1. Now let's see another term called entanglement. So entangle means that if there are two qubits, they are somehow very related, and if say one of the qubit is say red A, then the other one will surely be blue B. That means if I toss a coin and toss two coins, they are irrespective of how far they are. If one of them is heads, the other one surely will be head, and one of them will be tail, the other one surely will be tail. So if one of them is in one state, I know the other one will be just in the opposite state. And this helps to create the next generation of secured communication. We'll talk more about that in the and also a next generation of communication over a distance possible now. So in entanglement, we are saying that we're talking about first two qubits, and if one qubit is in a particular state, the other will surely be in the other state, because they are connecting to each other. To an extent, this is also defying the laws of the light, where Einstein once told that no particle can travel beyond the speed of light. That means the communication cannot happen beyond the speed of light. But here we're talking about, say, two different qubits at completely two different places, but they are kind of communicating without the qubits transferring, but they're communicating because if one of them in one state, the other one millions of kilometers away will be in the other state, and they are quite connected to each other, irrespective of the distance there. So this is another interesting thing in quantum world, where entanglement helps two different qubits to be kind of connected in a way, irrespective of how far they are. And let me just give you some example of this. One of this example is called teleporting. So teleporting means that, okay, I through an satellite channel, these two entangled qubits, one I have put in one part of the world, another I have sent to the other part of the world. And if something changes here in this first qubit, the other one will automatically change irrespective of the distance. So one, there is no physical transmission of bits that are happening, or electrons or photons that are happening. That way it can travel, the communication is happening beyond the speed of light. Second, I'm talking about a completely secured communication, because if somebody tries to eavesdrop and change something in between, the other will surely know, because the state on the other side will also change. So it is giving you a secured communication over a very large distance using a quantum teleportation. And this was tried in 2017. This is a public information. In China, they have created this quantum satellite communication called Messias satellite, where two different communication entities, which are 1400 kilometers apart, could use this quantum teleportation to help in this kind of communication. So this is another basic construct of communication, where using entanglement, where two qubits are related to each other, if they are sent to the two different part of the world, and even maybe tomorrow they can be, one can be in Earth, another can be in Mars, and if and the communication can happen faster than light, or we call it as an instantaneous communication. So this is another important thing in quantum world that is coming in. Okay, so So there are so many magical, interesting things in quantum communication that we have seen. It is kind of helping you to have millions of kind of computation of the classical computer done in just seconds in an instantaneous kind of computing, where all of them can be tried at once. We have seen quantum entanglement and quantum teleportation, where there can be instantaneous communication that can happen across a large distance. But why then we are not starting to use quantum computing and the quantum communication already in our day-to-day world? One is that quantum communication is still in the labs in a very, very controlled environment, and because they are very fragile. So the quantum states are highly sensitive to the noise, to the surrounding, and it needs a complete stable environment to operate. And giving this extremely precise and stable environment, it is very costly and very difficult to do. Like in a world like us, where there's so much of noise due to weather, due to different other conditions. Again, today the communication that is happening through the quantum channels are very limited. You saw that DRDO example. So this was only few kilometers that is possible there. For example, yeah, in the DRDO example, they have done this free space communication for 1 kilometer, and in a fiber like channel you can have 100 to 200 kilometers, not more than that. After that it will fade out because of sunlight and air movement and so on. Another is the signal amplification. So there is no boosting that is possible. You cannot copy a quantum bit and give it to somebody else. It is not possible to clone. So there is a no clone theorem, and that is because of the security enhancement that it has. So you're not allowed to clone anything in a quantum world. So if you're not unable to clone, you cannot amplify. You cannot have yeah, kind of amplifiers which can just copy it and send to the other part. So you cannot just amplify and send it to long distances. Third is the immature quantum repeaters. So there are quantum repeaters that are in works, which can help to create this repetition for a longer distance that it can travel. But these quantum repeaters are at very, very initial stage, and they are not mature enough to work. And if I sum all of them together, it is a high cost and poor scalability of the quantum that is still holding it back to become mainstream. So I'm saying that 10 to 15 years we still have in works before it can be a reality. Even in 6G, we'll not see, maybe it's far beyond that. But this is something because of the promises it brings in, and that I will talk about in the quantum communication examples, that the immense promise and the power quantum technologies are bringing, that's why we cannot just move away, or we cannot ignore quantum technology. It has to be researched on. That's why investments are happening and so on. Okay, so I've talked broadly about all the different pieces of quantum communication. Let me just talk about some of the key technologies that are driving the quantum world. So there are three things that we should know about the quantum technologies. One is the quantum computers. We are all hearing about IBM, Google, and all that creating this quantum computer. So they are using the quantum properties like qubits to do communication very fast. We saw an example of the password cracking in the previous slide. So this is one example of how fast it can do a processing. So we're talking about extremely fast computers that will have that the classical computers, even the supercomputers of today, will never be able to match. Second, we're talking about a quantum communication And this quantum communication is about securely transmitting information using superposition, using quantum teleportation and entanglement that we have seen, that we are controlling the photons in a way that we can do a super fast, super high speed communication. And the other is the quantum sensing. That means those atomic clocks, the clock that has microsecond level accuracy, and that can work even when there is no gravity. So that kind of clocks and that kind of this technologies, if they have to be powered, we need quantum sensing for handling or for measurement that are extremely sensitive to disturbances. So these are the three technologies that we should know about when we are talking about quantum technologies. Just not quantum communication, we have quantum computing, communication, and quantum sensing. But okay, so we are more interested in quantum communication. So in a very, very high level, in a quantum communication, what happens, there is a source which can send us a qubit. There is a destination or a receiver which can receive this quantum qubit, and they will use the quantum channel that is working in the principles of the quantum theory. The superposition, the entanglement, and the teleportation that we just saw in that satellite communication, that this will be the quantum channel, which can be a optical channel like the photons going there, or it can be a free space channel, the DRDO example that we saw in the beginning. So this is another example where that free space combination can be used for quantum channel also. So we need a quantum source, we can send qubits. We need a quantum channel which can use a free space or optical fiber to transfer these qubits, and there is a receiver which can receive this quantum channel. Okay, so now we'll go a little bit deep into the quantum communication, what this quantum communication is, because the other two are not very interesting or not the part of the scope of this discussion at least. So in quantum communication, we have, of course, the quantum networking, the network that will help to communicate. But there are a few other things that we should know. One of the important thing of quantum communication is security. That means a security that is way beyond the cryptography that we know today. That means even if the quantum computers are there, which can crack the secured keys of today, cannot crack the keys which are created through these technology. So what are these? The first one is the quantum random number generator. And this is something, by the way, used today. Even the Samsung Galaxy phones are using this quantum random generator. So this quantum random generator helps you to create those secured keys that can be used for the communication or encrypting the signal before they go out of those phones, for example. So the quantum random generator is a technique used to create the keys. Then we have the quantum key distribution. This is one of the most important mechanism, where maybe through an example of entanglement that we saw earlier, and other mechanisms, it will create a key that is quantum safe. What does it mean? It means that today, say, how a cryptography works. Say, I will encrypt my message using a private key, and then I will send the public key to the other side, and the other side can use the or I will encrypt with the public key, and then I will use as send the public key and the communication my packet to the other side, and using a private key, the other side will open it. So it is encrypted with the public key, and the public key is known to everybody. But the thing is that they will not be able to open it because they don't have the private key. But in the quantum computing world, what will happen is that these encrypted data can be opened up, because the speed in which they can try out different examples. You saw that password cracking example. So the speed in which it can kind of compute and try out different combinations, it can crack the encrypted data of today. But the quantum key distribution is a way in which we're creating the keys which are quantum safe, and it cannot be cracked using the quantum computers also. Another is the quantum clock synchronization. It again is a technique for securing the data, where what we are saying is that we are using some high precision clocks, which are like synchronized using the quantum mechanisms like quantum sensing, so that if any kind of if like trespassing happens and somebody goes and sees what is inside, tries to see the intents, it will be immediately known to the sender and the receiver. And the final thing is the quantum networking, which is using all these technologies of security and the high speed communication that quantum can bring in, we are able to communicate. So let's a little bit see more into what this quantum networking is. Okay. So quantum networking will help us to create the quantum internet of the future. So what it is doing, it is connecting those quantum computers, which are high speed computers of tomorrow, using a very secure communication using maybe the QKD that we have just seen, that kind of highly secured communication that is highly distributed, that can be millions of kilometers away thanks to this quantum teleportation. So we're talking about different quantum computers which are talking to each other, which are very far away from each other, and the communication is so secure that nobody can just get into that and open it. So that is what the quantum internet will be. So we are talking about the classical internet today, and tomorrow we are going talking. We'll have the quantum internet. But will the classical computing and the classical internet will go away? No. For example, we have the CPUs, we have the GPUs. When the GPUs came in, the CPUs didn't go away. For the high speed computing, we are using GPU like the AI, and for the normal computing, we are still using the CPU. Like my laptop has a CPU on which this communication is happening now. Similarly, the quantum internet will be used for very high speed kind of distributed computing and distributed communication, but the classical computers and the classical internet will still be there. And this quantum internet will use this qubits, the superposition and entanglement to transmit the quantum state securely using the photons in a fiber or in satellite link. Some of the things that we will see that will come in the future is like the quantum repeaters, routers, memories, and entanglement out there. So these are the things that will help to create this quantum internet. So we are getting into an era of quantum internet where the quantum computers can talk to each other very securely. So we're talking about security a bit. So let me just get into this, what this quantum key distribution is, which is quite talked about now. So quantum key distribution uses a protocol called BB84 because it was first like invented in 1984. So it securely helps to exchange the key via quantum state. So as I said that the what happens in a encryption, the messages are encrypted using using a public key, but it cannot be opened with the same public key. You need to know the private key on the other side to open it. And these are so secure that today's classical computers cannot open it. But uh, tomorrow's quantum computers can open it because they are very fast. So but if we have the quantum key distribution, it will not it is a mechanism of distributing these keys similar to how we are doing classical keys, but these keys and the messages which are encrypted using this key will you'll never be able to open using even the quantum computer. So some of these QKDs are already deployed today in China, Europe, and now you're seeing even in India they are doing it. So why they're securing with the quantum key distribution when we are not even having the quantum computers mainstream? Let me give an example. Say the defense installations, they will never change for centuries. For example, the air bases that you have, the naval bases you have, your army deployment that you have, so those will those remain there for several decades. So what these hackers are doing, they are just copying the communication that is happening between the different defense units, for example, or sensitive information that is happening. They know they cannot crack it today, but they will wait for next decade or so. When the quantum computers will come in, they will go and use the quantum computers to decode them and understand what the information. The information then will still be valid because this information don't change, because I said these are information, they hardly change, and because they are your defense information, they remain same for several decades. So this is the threat because of which the even today the QKD is being used for securing the communication. You saw some of the examples already. So QKD helps us to use a way to securely send the keys and use this keys to have a quantum safe encryption out there. Okay, so we talked about the quantum communication. We talked about the technologies behind the quantum communication. We talked about the quantum internet, that will be a distributed set of quantum computers that will use this quantum communication principles to communicate with each other. So one thing that I want to now emphasize is that what we as Capgemini is doing. So we as Capgemini, we are contributing to this quantum initiative already. Well, one of the main thing that we have where we are like trying out the different thing that we just saw in the previous slide is the our global Q labs. You will find a lot of information in a public domain about the Capgemini's Q lab. So these are like very high-end labs in India, UK, and Portugal, where the different quantum computing, communication, and sensing technologies are being tested there. And our India lab is in Bangalore, and there's some recent news also about like the work that we're doing out there. Second is your the IBM Quantum Hub partnership. So we are one of the exclusive partner of IBM Quantum Systems, where we are able to create a different high-end quantum-based applications on the IBM quantum clusters. So that helps us to do research on the real computer, not just on simulation. Again, we are in the frontline research. For example, there are several EU-funded programs on quantum computing, quantum communication. We are participating, like the equality program that we are leading as Capgemini, the DAPRA projects on energy and climate challenges that we are trying to solve using quantum computers. We are partnering with our clients to create future ready security, like how the post quantum cryptography will work and secure against next generation threats, all those different quantum communication security and QKD and other things that we are researching on. And we are also doing a lot of client-centric innovation, enabling quantum adoption across the key industries with end-to-end services. So we're helping our customers to also embrace this without any problem. And the way we are doing is that we are helping them to realize those different quantum security use cases to start with, and test other quantum communication principles in their network. So, in summary, Capgemini has a lot of research, industry partnerships, and the use cases, mainstream use cases that we are bringing it to the industry with our partners and academic collaborations to make progress in the research of quantum computing. So, in conclusion, I want to say that the quantum communication is a little bit far away, but it it is a complete paradigm shift that we're talking about. How we are transmitting communication. We are talking about communication that is instantaneous, which can beat the speed of light, not because transmitting faster than light, but because of the quantum teleportation that we have seen. It will be ultra secure, which cannot be broken. We have seen quantum key distribution principles, like that will create a complete unbreakable security. So, and then we saw that quantum communication and its principles will be the founding technologies for quantum internet, the internet of tomorrow, to connect these quantum computers, high speed, secure at large distance. And we have seen that India is already advancing with different trials in quantum computers, like um, we are seeing that this free space communication, and before that there were some optical communication that were tried for defense and otherwise. We have a national quantum mission and different academic partnerships like with IITs, which are helping us to do that. And in the world also, like China, we have seen that quantum teleportation. Uh, that China created through the quantum satellites, and the other large use cases that are being driven in US and Europe that are helping to make progress in this quantum communication world. For example, USA is saying that they will have the first quantum internet ready by 2035. And we are also seeing that like the large system integrators like us, like Capgemini, which are who are also helping this industry to embrace quantum computers with our leading research and the use cases that is meaningful for our customers and for this system. So I will finally end up with a quote from famous quote from Werner Hensberg, who is one of the pioneer scientists. He said that not only is the universe stranger than we think, it is stranger than we can think, and that's what we are seeing with the quantum computers. So thank you so much for listening me. If there is any question, please let me know.
Thank you, sir. Thank you so much for the enlightening session. Yes, there are questions by the participants, which I like to now take up with your permission.
Sure, please go ahead.
So, first question we have: can quantum key distribution actually help in banks, especially to protect money frauds?
Absolutely. So any communication that happens through these wires in a long distance, that can be secured, and bank and the financial system is one of the leading areas or use case where this quantum key distributions will be used. And as I said, that they will not be used after 10 years. They're being used now because some of the informations can be like collected now and can be decrypted when the quantum computers come after 10 years. So we have to be secured against the quantum computers even if they're not there. And banking is one of this area where we'll highly need this kind of technologies.
Sure. So, next question we have. One fundamental challenge, as you also discussed, of quantum communication is long distance transmission of the quantum states. So, how successfully have we overcome this, especially, I would say, in long range applications?
Yeah, so this is still a challenge, and it is something being tested now. You have seen that DRDO and IIT Delhi example. So they have done a communication of 1 kilometer using free space. And now this can be further used along with the entanglement or the quantum teleportation to have a longer distance communication. We saw that example from China's quantum satellite use case, where they are using quantum teleportation to have 1400 kilometers distance in which they are communicating. So we'll see gradually things improving, things where we can have communication to a longer distance, but it's still, I will say, is not mainstream. It will take several years before coming there, but we are taking tangible steps toward doing that.
Absolutely. So, one last and I would say very important question. Uh, how can quantum communication help customize the healthcare domain? Like, can we have quantum empowered sensors, etc.? How far are we from this?
Yeah, absolutely. For example, in fact, I will give you an example of COVID-like pandemic. It took us 1 year to get a vaccine for that because of the limitation of the current computers. So when you are doing a drug discovery, this AI system play a very big role to find out the different molecular behaviors, to learn that different DNA patterns which has to be analyzed to understand what is the drug and how the drug will be created. So from the start of the pandemic, the first vaccine I think came after 8 to 12 months. Had there been quantum computers, it had been much faster to do that. So one of the big example is to create those different simulations of DNAs and molecules to through the quantum computers, which will make it much faster and much cheaper to create those kind of drug discoveries possible.
Absolutely. So, one another question I can see from one of our panelists: is there any role or contribution of Gen AI in quantum computing?
Okay, I will say it is otherwise. I will say that maybe the Gen AI will use quantum computers and the quantum communication because as you're seeing this foundation models like the large language model, large vision models, and other foundation models that we are seeing today, they need immense amount of computing power. To use to create this model. So if you have to train, fine tune this model, that needs immense amount of computing power. You might have heard that to power this kind of systems, even Google data centers, they're going for nuclear energy because immense amount of energy that is required to power this large system. So I will say that quantum computers will make this not only faster, it will make it much more sustainable, because with less power, these quantum computers will be able to do many more combinations possible. So that way the GenAI will be leveraging quantum computers to help that. And the other side, if I see, if to answer your specific question, how GenAI will help quantum computers. So with GenAI or generative AI, we'll have new use cases with quantum computers which are not possible today. I will give an example. Say today, the population of this world is just increasing and increasing. For example, India is having the largest population in the world, but our agricultural land is limited. We cannot have more land as we have more people. So after some time, there'll be shortage of food if we go with the same technologies that we are using today for agriculture. So we have to find different other technologies that are required to grow more crops in volume and in quality in the same piece of land that we have today, to feed many more millions of people than today. So for that, generative AI can help using the quantum computing power to generate this kind of different say suggestion technologies and the different mechanism that can help us to grow crops with the newer technology, with which is much more higher in quality and much more in volume, that can feed the people with the same piece of land. So both ways it's possible. The generative AI will get benefited with the higher compute power of the quantum computing, and quantum computing will also get benefited by generative AI, because the new set of problems which we are not able to tackle today, like the agriculture problem with the growing population, that will be also be tackled through generative AI on quantum computers.
Absolutely, sir. Very well answered. And thank you so much once again for this wonderful session today. And we hope to have many such more informative sessions with you in the near future. So please accept this certificate from our side as a token of remembrance for this wonderful session today. Huda sir could not be a part of this session today. He was busy in some meeting, but it's actually been a wonderful session. Thank you so much, sir.
Thank you so much for having me.
And so we also have a small e-memento. So once again, thank you so much, Shubhankar sir, today for this wonderful session. The simplicity with which you have explained the quantum computing and how this quantum age is, I would say, being applied to especially these connectivity applications has been actually wonderful. Thank you so much.
Thank you. Thank you.
Thank you, sir. So, dear participants, with this, we come to an end to this wonderful session today on quantum computing. The feedback link for the same has been shared with all the participants in the chat window. I request participants, please click on the feedback link, submit your details. Please fill in your details carefully because any mistakes you make, they directly get reflected into your certificate. So please submit your details carefully. And as soon as you submit your details, your e-certificate for this webinar would be auto-generated and mailed to your inbox. So please stay in this room till the time you do not receive your certificate for this webinar. Once you receive the same, you're most welcome to log out of this meeting room with a promise to join us back next Saturday with another important webinar of ours on another new and I would say upcoming technology. So thank you so much, all dear participants. It has been a wonderful session today. And I thank you, all of you, for joining the session. Please mark your calendar to join us next Saturday once again.
Okay, thank you, Dr. Ritika. It was a
Thank
great
you,
session.
sir.
Thank you. I'll drop. It was a great session indeed. Thank you.
Thank you, sir. Thank you so much, sir.
Bye.
Okay, sir. Dear participants, I hope everybody has submitted the feedback form. We will be closing this meeting room in another 5 minutes from now. So any participant who has as yet not submitted the feedback form or has not received their certificate of participation, please ensure that you submit the feedback form to generate your certificate of participation. In case after submitting the feedback form, you have not received the same, please ensure, dear participants, that you share your email ID with all panelists in the chat window. We are there to help you out with the same. But in case you do not receive your certificate and the room closes, we'll not be able to help you after that. So in case you have submitted the feedback form and have as yet not received your certificate, check your spam folder or share your email ID with all panelists in the chat window. I still have Dr. Mohammed, Harshid, Kamlesh, Mohammed Moeddin, Nitika, Partha Sarthi, Prashant, Rahul Sethi, Tarushi, and Vivek. I hope they all have received their certificate and have only forgotten to leave the meeting room. Dear participants, we'll be closing this meeting room in another 2 minutes from now. So please ensure that you have submitted the feedback form and generated your certificate of participation.
Nitika ji, can I get your mobile number?
Sure, sir. I'll message you in the chat.
My phone number is there now with you.
Okay, sir.
Okay, right. Okay. What happened, Oda sir, today? Busy?
Yes, sir. Sir was busy in a meeting.
I see.
Dear participant, this is the last call. In case any one of you has as yet not submitted the feedback form, please do so. Once we close this meeting room, you will not be able to generate your certificate. I still have Harshit, Kamlesh, Mohammad Mohiddin, Nitika, Parthasarthi, Prashant, Rahul, and Tarushi with me. I hope they all have received their certificate of participation after successfully submitting their feedback form. And I've only forgotten to leave this meeting room. Thank you so much, all dear participants. I request you all to please note next Saturday is our next webinar. Do join us on that webinar.